Markov chain is a mathematical tool to analyze systems with a finite set of states. The system can transition between different states with some probability. For example, the traffic light. We know that the traffic light has exactly 3 states: red, yellow, and green. And we also know that in the next run, it has exactly the same 3 possible states: red, yellow, and green. And we can model the transition between this run and next run of the traffic light by a 3x3 matrix. We call this matrix a transition matrix. So let's look at it. Let's suppose that the traffic light shows red at this moment. What's the probability of it still being red in the next round? 0, because we know it cannot stay red, otherwise the traffic will be stopped effectively. And what's the probability of red being transitioned to yellow in the next round? Also 0, because we know that red cannot turn yellow, it can only turn green, so it's also 0. What about green? Well, it's 100%, because we know that red light 100% inevitably transition to green in the next round. So for the current state of red, it has 3 probabilities, 0, 0, 1. They add up to 1. Great. Similarly, we can write the entries of the yellow column. It's 1, 0, 0, because we know that inevitably yellow transition to red, so we put 1 there and 0 elsewhere. Similarly for green, it's 0, 1, 0, because we know that green can only turn yellow, so it's 0, 1, 0. Now we have completed all the entries of the transition matrix, and as I mentioned earlier, it has a special property that the sum of the entries of each column must add up to 1. That is because for each possible current state, the probability of a transition to the other ones must add up to 1 as a basic concept in the probabilistic theory. To represent the state of the system, we use the 3 vector in this case because we have 3 possible states: red, yellow, and green. Let's say that the light is red, then we write 1, 0, 0, as we 100% sure that the current light shows red. How do we use it? Well, we can multiply the transition matrix and the vector to get the next round, to get the state of the traffic light next round. Let's name the transition matrix P and the vector X. So the current state will be 1, 0, 0. The next state will be P times X, and that will be 0, 0, 1, meaning the light is green. That's absolutely right, because we know that red will inevitably turn green. What if we want to know the state of the system after 3 runs? We multiply x by p to get the state next round, and then we multiply the result of px by p again on the left to get the result after 2 runs, and then we multiply again by p on the left to get the result of the system after 3 runs. So we'll simplify it, we get p cubed times x. That will give us the expected state of the system after 3 runs. Let's change our notation a little bit. We write the initial state, the very beginning state of the system, as x naught. After first round of transition is x1, second run is x2, so on and so forth. We can also rewrite x1 as p times x naught, and that as we defined earlier, and we can rewrite x2 as p times x1. To generalize, we can write xn plus 1 as p times xn. However, we can also rewrite x2 as p times x naught. That's p squared x naught. And to generalize it, we can also write xn plus 1 as p to the nth power times x naught. Let's look at some other transition matrix that has something more than just 1s or 0s. Let's say that the weather of a day has 2 possible states, rainy or sunny. We can model the transition between 2 days by a 2x2 transition matrix. Let's say that if it's raining today, if the probability of it continue to rain is 0.8, and the probability of it turning sunny is 0.2. And if it's sunny today, the probability of it goes raining is 0.3, and the probability of it staying sunny tomorrow is 0.7. As we can see, this transition matrix also satisfies our property that the sum of the entries of each columns add up to 1. So what's the weather after 1 day, 2 days, or 3 days? Let's write it out to, a large number of days. As we can see, when the days go past 11, when it becomes large enough, the resulting state vector is all the same. It's 0.6, 0, 0, 0, 0, and 0.4, 0, 0, 0, 0. So it almost seems that it converges into a one specific vector. This is very interesting because this is saying that if we know the transition matrix and the initial state, the prediction of the weather after a large enough rounds will remain the same. If the initial state is sunny, we know that in the foreseeable future, the probability of it remain sunny is 0.4, and the probability of it became rainy in any specific day after the 11th day will be roughly 0.6. Does this happen to other matrix? Let's try it out. Let's just write another 3x3 transition matrix to satisfy our property. And let's say the initial state is 0, 1, 0. Voila! After 11 rounds, it happens to be 11 rounds again. The state will stabilize around 0.557, 0.220, and 0.213. It's the same vector after 12th, 13th, or 14th rounds. This is amazing. However, we know that this is not true for some matrix. Take the initial traffic light example. There's no steady state because we know that the traffic light alternates between red, green, and yellow. It does not converge into a specific state, no matter what the initial state is. So what kind of matrix have converging state vectors? After years of exploration, the mathematicians indeed found a specific set of matrices that have converging state vectors. They call it the regular transition matrix. How to define it? Well, if a matrix or some integer powers of it have all positive entries, then this transition matrix will be a regular transition matrix. The mathematicians also found that if you raise a regular transition matrix to a large enough power, the columns of the resulting matrix will be all the same. More importantly, each columns of this resulting matrix will be the converged state vector. And also, we can call it the steady state vector. Say we have a regular transition matrix. How do we find its steady state? How do we find the expected values in the steady state vectors? Well, let's check it out. Take a regular transition matrix P and a random initial state vector X. We have that the limit, as n goes to infinity, of P to the nth power times X equals Q, where Q is the steady state vector. So if n is large enough, we have p to the nth power times x equals q, and p to the n plus 1 power times x also is q, as the definition of the steady state vector and the regular transition matrix. Let's do some algebra. So from these two equations, we can have p times q equals q. This is amazing because we can rewrite Q as I times Q, where I is the identity matrix. We have P times Q equals I times Q. Rewrite it, we have P minus I times Q equals 0. This is familiar because that means that Q is in the kernel of P minus I. Let's see if it actually works. Take the matrix from the rainy day, sunny day example. We have 0.8, 0.2, 0.3, and 0.7. We know that it's a regular transition matrix because all of the entries, well, are positive. We call it P. P minus I will equal negative 0.2, 0.2, 0.3, and negative 0.3. We'll reduce it. We have 1, 0, negative 1.5, and 0. We know that the resulting steady state vector will be in the kernel of this matrix. So let's take this Q1 and Q2. We have Q1 minus 1.5, Q2 equals 0. We're stuck. Well, no, because we know a special relationship between Q1 and Q2. That is, they add up to 1. For any state vector, all the entries add up to 1. So we can rewrite the equation as 1 minus Q2 equals 1.5 Q2. Solve it, we have Q2 equals 0.4 and Q1 equals 0.6. That exactly matches what we get if we raise the power of the transition matrix to 11th power and times it with any initial state. Let's try this method out again with the matrix from the traffic light example, which we know does not have a steady state because the traffic light alternates between three states, red, yellow, and green, and does not converge into a specific state. We have P minus I equals negative 1, 0, 1, 1, negative 1, 0, 0, 1, negative 1. We'll reduce it. we have the identity matrix. That means the kernel is 0. That means there is no such vector that makes p minus I times this vector equal 0, which is correct because we know that this matrix does not have a steady state vector. The Markov chain has a wide variety of applications like machine learning and decision making, and one of them is Google page ranking.